Aloha BIOCHEM. In this fourth and final lecture for Chapter 5, we discuss chemical equation calculations. So in this video, we'll touch on the remaining sections in the chapter, 5.7 to 5.10. Now, we've covered chemical reactions in pretty good detail. In the previous 3 videos on Chapter 5, we introduced chemical reactions and we balanced their equations. We categorized all of the reactions into, different categories. We even covered redox reactions pretty well. And we also did some calculations involving the chemicals that are involved in reacting in the last video. In this video, we're going to expand on what we just did and do some calculations on chemical reactions themselves. Now, here's the chemical equation for a reaction that we've seen before, the combustion of methane. And this is a balanced equation, so we can interpret it as follows. 1 mole of CH4 gas, that's a methane gas, reacts with 2 moles of oxygen gas to produce 2 moles of water gas and 1 mole of carbon dioxide gas. These coefficients in the balanced equation tell us the amount of chemicals that are reacting and that are also being produced. And we can use them to get certain relations that are needed in chemical equation calculations. And these relations are as follows. If 1 mole of methane reacts, then that means that 2 moles of oxygen must also react. The ratio is 1 to 2. And when you have this happening, you also have 2 moles of water being produced, and you also have 1 mole of carbon dioxide being produced. That should say CO2. So we can kind of think of these as equalities. 1 mole of CH4 reacts is equal to 2 moles of oxygen reacting. If you have this, then you also have that. And you also have that, and you also have that. And it's kind of like a bunch of relations built into here. If you have 1 mole of methane reacting, then you have 1 mole of carbon dioxide being produced. And if you have 2 moles of water being produced, then you must have had 2 moles of oxygen reacting, according to this reaction. So you have lots of relations built in here, and we can use them in calculations. And so what we're going to do in this video is do several examples of chemical equation calculations, and we'll use lots of the relations that are here. And we'll start off easy. In the first example, we'll do a mole to mole conversion, which is a simple one-step conversion. And we're asked, how many moles of O2 are needed for 4.5 moles of CH4 to react? So we're asked for the moles of O2 that are needed for this many moles of CH4 to react. So we're going to need this relation right here between these 2 chemicals. 1 mole of CH4 reacts means 2 moles of O2 reacting. And so this relation is copied down right there. Now we're given 4.5 moles of CH4 reacting, and so we can use this relation to convert from moles of CH4 reacting to moles of O2 that are also needed to react. And we do it as follows. We take the relation and we use it to build a conversion factor, as we've done so many times before. We start with our 4.5 moles of CH4, and to get moles of O2, we put that on top, and we put the 1 moles of CH4 down on the bottom. You see the moles of CH4 canceling, and you're left with moles of O2. And the numbers calculate 4.5 times 2 gives you a 9. Now, this should make sense. If you have 4.5 moles of CH4, you need 9 moles of oxygen. because the ratio is 1 to 2. You need twice as many moles of O2 versus CH4, and 9 is twice 4.5. Now, during combustion reactions, the oxygen is usually in excess. When you're burning something, oxygen is usually in excess because you're burning it in the air. And so although you only use 9 moles of oxygen, there'll be a lot of oxygen left over in the air that's unused. Okay, this is just the amount that's used. Our next example is a little more complicated. Here we'll do a mole to gram conversion, and this will be a 2-step conversion. And we're asked how many grams CO2 are produced if 4.5 moles of CH4 react. Now, here we're going to assume that there's excess oxygen available, as there usually is. Okay, it would be a totally different situation if you only have a tiny bit of oxygen. Well, then all of this might not burn in the first place. But if you have enough oxygen, then all of this will react. Okay, so if 4.5 moles of methane react, how many grams of CO2 are produced? Now here, the relation is between methane and CO2. Okay, methane and CO2. 1 mole of methane reacting means 1 mole of CO2 being produced. Okay, so I'll copy down this relation right here. 1 mole of methane reacting means 1 mole of CO2 being produced. And so we can convert moles of methane to moles of CO2, but we're asked for grams of CO2. Now, if we can get to moles of CO2, then we can convert moles of CO2 to grams of CO2 using the methods in our last lecture. Okay, we need the molar mass. We need to know how many grams is a mole for CO2. And that is pretty easy to get using the periodic table. So I'll remind you, for carbon dioxide, you have 1 carbon and 2 oxygens. And so you look up carbon. Its atomic mass is 12.011, and oxygens is 15.999. So you add 1 of these plus 2 of those, and that calculates to be 44.01. Okay, and so we know now that 1 mole of CO2 is 44.01 grams of CO2. And this will let us convert from moles of CO2 to grams of CO2 so we can answer the question. So we put this together as follows. We take our 4.5 moles of CH4 and we start off with that. And using the first relation, we get to moles of CO2. And using the second relation, we get to grams of CO2. So you can see the cancellation. The moles of CH4 cancel, the moles of CO2 cancel, and this is a 2-step conversion, and we're left with grams of CO2. And doing the calculation, 4.5, a bunch of 1s, times 44.01, you get 198.045 grams of CO2. Now this will round to a 2 sig fig result, and so you're going to round it to this position, so it's going to round up to 200. And so 200 grams CO2, and the underlining will tell you, kind of tells you that this is the last significant figure, but technically you're supposed to convert it to scientific notation, to indicate, okay, it's just a 2 sig fig number. But if you say 200 grams and you underline that 0, I'll know what you're talking about. Okay, so this many grams of CO2 is what you should get if 4.5 moles of methane react. So we'll call this the theoretical yield. So if you burn 4.5 moles of methane, then theoretically that's how much CO2 you should get. We just calculated it. Okay, we didn't do the reaction. If you do the reaction and you collect all of the carbon dioxide at the end, you should get something pretty close to this, but usually you'll get a little bit less than the theoretical yields because you always lose chemicals in the laboratory. So your actual yield is always a little bit less than the theoretical yield. So as we do calculations, we're calculating the theoretical yield. Just be aware that when you do things in the laboratory, you might not get everything that you expect. Okay. In our next example, we're going to do a gram to gram conversion, and this will be a 3-step conversion. And this is another excess reactant problem. We just did one. We assumed excess oxygen is available, so we're going to do that again. This time, we're going to ask how many grams of water are produced if 10 grams of methane reacts. And we'll assume excess oxygen is available. See, so now we're given the grams of methane and we're asked for grams of water. Okay? And so to get from methane to water, we need the methane-water relation. That's a 1 to 2 mole relation. Okay? So the way we're going to do this, well, let's copy this relation down. We're going to need it. It's a 1 to 2 mole relation, but we start off with grams of methane. We have to take our grams of methane and convert it to moles first, and then we can use that relation to get to moles of water, and then once we know moles of water, we get back to grams of water. To go from grams to moles and then moles back to grams, we need the molar masses of CH4 and also water. And you can look up on the periodic table, look up carbon and look up hydrogen. So 1 carbon plus 4 hydrogens. I'll point that out to you real quick. So you got 4 times this number, and then plus 1 times that number. And that calculates to be 16.043. So for methane, 1 mole is 16.043 grams. And then for water, you got 2 hydrogens, 1 oxygen. So you have 1 times oxygen's atomic mass plus 2 times hydrogen's atomic mass. And that calculates to be 18.015 grams. So 1 mole of water is 18.015 grams of water. Okay, now we have the relations that we can use to answer this question. If we have 10 grams of methane, then we use the first one to get from grams of methane to moles of methane. And then the balanced chemical equation gets us from moles of methane to moles of water. 1 mole of methane gives you 2 moles of water. And then the molar mass of water gets you from moles of water to grams of water. So it's a 3-step conversion this time, and we use these 3 relations to build the 3 conversion factors, and you can see the units canceling, and we're left with grams of water. And the numbers, 10 divided by 16.043 times 2 times 18.015, and you calculate 22.458 grams of water, which rounds to 22.5 grams of water. Again, the theoretical yield of water in the laboratory, you might only collect 20 grams of water. Okay, maybe a little bit less because you lost some of your chemicals. They always fizzle away in the air. You lose them. There's nothing you can do to stop it. It's almost impossible to get the full theoretical yield. If you do, you're a really good chemist. Okay, so the next example is what we call the limiting reactant problem. And compare this one with the last one. Okay. How many grams of H2O are produced if 10 grams of CH4 reacts with 10 grams of O2? So you see, this time we're not assuming we have excess oxygen. We're just going to give it 10 grams of oxygen. Okay? So maybe that's enough oxygen, I don't know. Maybe it's not enough oxygen. Okay, it's kind of like you want to burn some methane, but you want to do it inside of an enclosed container, and so it might all burn, it might not. There might be enough oxygen. Basically, when you have a certain amount of this reactant and a certain amount of that reactant, well, one of them's going to run out. Okay? One of them's going to run out, and it's going to limit the amount of product that you form. So it's called the limiting reactant problem. And the other one will be in excess. So we're not sure which one is in excess and which one runs out. And since this is a gram to, grams of water, you're asking for grams of water given grams of reactant. This is a gram to gram conversion. It's going to be another 3-step conversion, but the limiting reactant problem is best done, just doing the calculation twice. First, we assume all of the methane reacts, and we calculate how many grams of water that would give. And then second, we assume all of the oxygen reacts, and then figure out how many grams of water that would give. And so we do the calculation 2 times, and it turns out that one of these is going to be the correct answer. So we'll do the calculation just like we did before, but we'll do it twice, for each reactant. Okay, first of all, assume all of the methane reacts. It may or may not react. Okay, just say that it does, and let's see what happens. We take our 10 grams of methane and we calculate how many grams of water. Now, we just did this in the last problem. If you have 10 grams of methane, how many grams of water? This is how you do it. And so I've just copied that down right there. That's how you do it. Okay, so if the methane reacts, you should get 22.5 grams of water. Now, what about the oxygen? Let's assume all of the oxygen reacts and calculate how many grams of water that gives. So starting with 10 grams of oxygen now, let's convert oxygen to water. Now for this one, we're going to need the oxygen-water relationship. This is a 2-to-2 ratio. Okay. So take 10 grams of O2, okay, and the molar mass of O2, converts grams to moles. Oxygen is 15.999 or 16.00. And so you have O2, you have 2 of these, so that's 32. Okay, so the molar mass of O2 is 32. So 32 grams is 1 mole. So this gets you from grams to moles. And then to get from moles of O2 to moles of water, you use the 2-to-2 ratio in the balanced chemical equation. And to get from moles of water to grams of water, we use the molar mass of water again, just like we did up there. And you see the units canceling. Grams O2, grams O2, moles O2, moles O2, moles water, we're left with grams water. And the numbers give you 5.63 grams of water. It turns out that this is the right answer, and that's the wrong answer. When you do the limiting reactant problem and you calculate using both reactants, the one that gives you the smaller amount of product is the right answer. You see, when all of the O2 reacts, it's enough to give you that much water, okay? And then you don't have any more oxygen, okay? So you can't form any more water than this. 10 grams of oxygen gives you that much water. Now you have enough methane to get 22.5 grams of water, okay? But you don't have enough oxygen to get that much, okay? So the oxygen limits the amount of water that you get. So this is the correct answer, And the methane was enough to make the reaction go even further and further to get you 22.5 grams. Okay, so that was an excess. The methane is the excess chemical, the oxygen is the limiting reactant. It was kind of hard to see that just looking at the two in the problem. So we had to do the calculation to see, yes, it's the oxygen that limits the amount of product this time. So this is the theoretical yield here. Okay, so that's a good way to do the limiting reactant problem. Just do it twice. And the smaller number is the correct answer, and that will tell you what the limiting reactant is. Now, most of the time you do get less product collected than what you expect. Okay, if you do chemical reactions in the laboratory, things always happen. You know, if you burn stuff, you know, some things will fizzle away in the air. If you do reactions in solution and you try and collect the chemicals that are dissolved in the water, well, sometimes things remain dissolved in the water, and or you just, maybe you spill something, you always get less than what you expect. And so one way to quantify how much you got is to just calculate the percent yield. And this is calculated as your actual yield that you actually get in the laboratory divided by your theoretical yield and times 100%. Now the theoretical yield is like a maximum amount, okay? And the actual yield is always less than the theoretical yield. And so when you calculate your percent yield, you don't get more than 100%. You might get like 90 or 80 or 70. You know, the higher the percent yield, the better. Now to illustrate this, let's do the following reaction. This is one of my favorite reactions. Fermentation. Suppose 125 grams of glucose, sugar, reacts according to the chemical equation below. Calculate the theoretical yield in grams of ethanol produced. If only 58 grams of ethanol are collected, then calculate the percent yield. So here's the reaction. You have glucose, which is C6H12O6. It's dissolved in water. And this is a molecule of glucose. It's kind of complicated looking molecule. You have a ring, you know, oxygen, and then 5 carbons form a ring. And then this carbon has a hydrogen and an OH. This one has a hydrogen and an OH. This one a hydrogen and OH. This one hydrogen and OH. And this one gets a little bit longer branch coming off. But altogether, this is a glucose molecule. So kind of a big molecule. Now, this solution right here, when you dissolve glucose in water and you add a little bit of yeast to it, it's like sugar water. If you put a little bit of yeast in your sugar water, then the yeast will go to work. They will chew up your sugars and they will produce ethanol and carbon dioxide. And so this is the chemical reaction. This is used in fermentation. And it's used to make wine, beer, and spirits, and also root beer. So I'm a root beer guy, and I like making root beer, and so, you know, along with the sugar water, I put roots in there to flavor it. And so you get your bubbles, you know, your carbon dioxide bubbles, and a little bit of ethanol, you know, and root beer, you don't make it very alcoholic. If you're after more alcohol, then you let it ferment for longer. You let the CO2 escape, and as your alcohol level builds up, eventually you'll seal the bottle to get it carbonated, and so that's how you get more alcohol. But root beer, you just produce a little bit of carbon dioxide, and you have a tiny bit of alcohol in there. Anyway, suppose 125 grams of glucose reacts. So all of it reacts. And it forms products. Okay, and these are the two products. You're asked to do two things here. Calculate the theoretical yield in grams of the ethanol, and then if only 58 grams of ethanol are collected, then calculate the percent yield. So this is kind of like if you go in the laboratory and you get your ethanol, you're going to get less than your theoretical yield. So this is the actual yield here. So first calculate the theoretical yield, and then if this is how much you actually get, then calculate the percent yield using that equation. So let's calculate the theoretical yield first using the methods that we did in the previous examples. To get from grams of glucose to grams of ethanol, we need the glucose-ethanol relation. 1 mole of glucose gives you 2 moles of ethanol. So here's that relation. 1 mole of glucose gives you 2 moles of ethanol. But we need to get from grams of glucose to moles of glucose before we can convert to moles of ethanol. So you use the molar mass of glucose, you add 6 carbons, 12 hydrogens, 6 oxygens, and that calculates to be 180.156 grams. So 1 mole of glucose is 180.156 grams. And so you can take your 125 grams of glucose and using the molar mass of glucose, get to moles of glucose. And then using the balanced chemical equation, convert moles of glucose to moles of ethanol, and then using the molar mass of ethanol, get from moles of ethanol to grams of ethanol. So ethanol's formula has 2 carbons, 6 hydrogens, and 1 oxygen. So you add all those up and you get 46.069 grams. So this will be a 3-step conversion. It's a grams to grams, so 3 steps. 1, 2, 3, and then we can do it as follows right here. We start with 125 grams of glucose. The molar mass of glucose gets us to moles of glucose. The chemical equation gets us to moles of ethanol, and the molar mass of ethanol gets us to grams of ethanol. Make sure these conversion factors are appropriately flipped. Okay, if you start with grams of glucose, you put the grams down here and the moles up there. Okay, and that cancels the grams. And then you see the moles of glucose cancels moles of glucose down there. And then the moles of ethanol must cancel moles of ethanol down there. So this time the moles go down here and the grams go up there. Okay, and you see the units all canceling. You're left with grams of ethanol. And do the calculation and you get 63.9 grams of ethanol. So that's the theoretical yield that you should form, or the maximum amount that you could form from the fermentation of 125 grams of glucose. Now the problem says if only 58 grams of ethanol are collected, then calculate the percent yield. So the max amount is 63.9, but we only got 58. So to get percent yield, it's actual over theoretical. So 58 over 63.9 times 100, and that calculates to be 91%. 91% is a pretty good percent yield in the laboratory. Okay, if you do chemical reactions and you collect 90% of what you're supposed to get, that's pretty good. In chemistry, in biochemistry especially, when drug companies make drugs, they need to do chemical reactions in multiple steps. In each individual step, they might only be getting 90% of what they're supposed to get. And so that loss adds up over the course of time. And so if you get 90% in the first step, and then in the second step you get 90%, and the third step 90%, all those percentages kind of add up, and then at the end you've lost quite a bit. And so pharmaceutical companies are very interested in methods that get them consistently in the 90 percentile yield. So this is pretty good percent yield. Now, a lot of calculations in this lecture, and I hope you're able to follow all that. In our next lecture, lecture 25 or 26, we will be moving into chapter 6. So we'll start off with an introduction to energy and discuss nutritional calculations. So stay tuned for that. Aloha.